Okay, next property is atomic radius. We know in transition series with increase in atomic number, the atomic radius decreases. That is, as we know, across the period, atomic radius decreases. But the decrease in atomic radius in transition series is not regular. There are some variations in this. As we are seeing, from scandium to chromium, atomic radius decreases. This is because of increase in effective nuclear charge. In D block elements, that is in transition series, the added electron enters into the inner n-1 d orbital. That is in 3D series, the added electron, the last electron enters into 3D orbital, inner 3D orbital. Here from scandium to chromium, the number of electrons in the inner 3D orbitals are less. That means the screening effect is less. That means the effective nuclear charge predominates over the screening effect. As we know, with increase in effective nuclear charge, atomic radius decreases, and with increase in screening effect, atomic radius increases. Here from scandium to chromium, atomic radius decreases due to increase in effective nuclear charge. But from chromium to copper, the atomic radius remains nearly the same. This is because here screening effect also increases and effective nuclear charge also increases. So, the effective nuclear charge is compensated by the screening effect produced by 3D electrons. And if we move towards the end, that is zinc atomic radius of zinc is large because zinc has completely filled d orbital, that is D10 configuration it has, and it has paired electrons, and the electrons repel each other, hence the electron cloud expands. And as we move down the group, atomic radius increases. So, the atomic radii of the elements of 4D series is larger than the atomic radius of 3D series elements. But as we see, okay, here you are seeing that the scandium to chromium atomic radius decreases, then from chromium to copper, that is nickel, atomic radius remains same, and zinc has large atomic radius. And here you see that is the 3D series and 4D series. The 4D series elements have larger atomic radius than 3D series. But the atomic radius of 4D and 5D series are nearly same. This is because of lanthanide contraction produced by 5D electrons, 5D series. That is lanthanide contraction observed in 5D series. About lanthanide contraction, you will study when you study the F block elements. Here, what are the consequences of this lanthanide contraction? What is lanthanide contraction and what are its consequences? About all these you will study when you study F block elements. Here, it is seen that 4D and 5D series elements have nearly same atomic radius. So, next property of D block elements is ionization enthalpy. As we know, with increase in atomic radius, with the decrease in atomic radius, Across the transition series from left to right, atomic radius decreases. So, but there are some variations as we have studied. So here ionization with the decrease in atomic radius, as the atomic radius decreases, ionization enthalpy increases along each series of transition elements, that is from left to right. But here also this increase is not regular and some variations are observed in the ionization enthalpy, in the increase in ionization enthalpy. What are those variations? Let us see. See, the first ionization enthalpy of chromium is lower than expected. So, chromium ionization enthalpy is expected to be high because chromium has stable electronic configuration of 3d54s1, but it has lower ionization enthalpy than expected. This is because here chromium has 3d54s1 configuration. So after the removal of one electron from 4d orbital, it gets a stable configuration of 3d5. That means 3d5 configuration, there is no change in d5 configuration. And then if we see the zinc, in zinc, the first ionization enthalpy of zinc is high because as we know, zinc has 3d10-4s2 configuration. The electron has to be removed from filled, that is stable 4s2 orbital. So high energy is required. Therefore, first ionization enthalpy of zinc is higher. Next, coming to second ionization enthalpy. Second ionization enthalpy of chromium and copper are higher because here the Cr3 plus and Cr plus and Cu plus configuration are stable. That is Cr plus has argon 3d5 configuration, that is half filled d orbital is there, and Cu2 plus has 3d10 configuration, that is completely filled. So here for removing second electron, the second electron has to be removed from stable 3d5 and 3d10 orbitals. So high energy is required. So the second ionization enthalpy of chromium and copper is high. Next, second ionization enthalpy of zinc is low because zinc Zn plus configuration, as we know, is argon 3d10-4s1. So it contains one electron in the outermost 4s orbital. The removal of one electron is easier because after the removal of this one electron, this Zn2 plus configuration will be 3d10. It gets 3d10 configuration. Stable configuration it gets. Therefore, the second ionization enthalpy of zinc is low. Now coming to third ionization enthalpy. The third ionization enthalpy of manganese and zinc are higher because as we know Mn2 plus has 3d5 configuration, stable configuration. Therefore, removal from this stable configuration, removal of electron is difficult. High energy is required. Therefore, the third ionization enthalpy of manganese is higher. Similarly, the third ionization enthalpy of zinc is also high because Zn2 plus has 3d10 stable configuration. So, for the removal of one electron from this stable 3d10 configuration, more energy is required. So this is about ionization enthalpy. Next property is oxidation state. What is meant by oxidation state? The charge assigned to an atom in its combined state is known as oxidation number. That is, the charge acquired by the atom of an ion is called as its oxidation number. Say oxidation number, these transition elements exhibit variable oxidation states. This is because during the formation of compounds, in transition elements utilize both ns orbital electrons as well as n minus 1 d orbital electrons for bond formation. This is because the energy difference between n minus 1 d and ns orbital is very less. So, in addition, anyhow they will use outermost 4s electron for bond formation during the formation of compounds. In addition to outer 4s orbital, that is ns orbital, they utilize n minus 1 d electrons also for bond formation. So, they exhibit variable oxidation state depending upon the electrons involved in bonding. See, as we see the oxidation state, scandium exhibit only +3 oxidation state, and zinc and scandium, these two elements exhibit only one oxidation states, that is scandium exhibit +3 and zinc exhibit +2 oxidation state. This is because scandium contains only one electron in the 3d orbital. So less electrons are involved. So along with the outermost 2 electrons, this one electron is also involved in bond formation. Therefore, it exhibits +3 oxidation state. Now, from scandium to manganese. From scandium to manganese, the minimum oxidation state is the number of electrons present in outermost ns orbital, and the maximum oxidation state is the sum of electrons present in 4s orbital and 3d orbitals. But from iron to zinc, the minimum oxidation state is same as, that is the number of electrons present in 4s orbital, but the maximum oxidation state is not the sum of electrons present in 4s and 3d orbital. It is the maximum oxidation state is equal to the sum of electrons present in 4s orbital and the unpaired electrons present in 3d orbital, because after manganese the pairing of electrons of d orbital starts. So as you are seeing here, scandium contains 2 electrons in 4s orbital and 1 electron in 3d orbital. Therefore, it exhibits an oxidation state of +3. Titanium exhibit oxidation state of +2, +3 and +4. Vanadium, it exhibits +2, that is the minimum oxidation state in all these elements is the number of electrons present in 4s orbital, and the maximum oxidation state exhibited by vanadium is +5, that is the sum of electrons present in 4s and 3d. Chromium maximum oxidation state is +6. So it exhibits the oxidation state of +2, +3, +4, +5 and +6. Manganese exhibits the maximum oxidation state of +7. So this is the maximum oxidation state exhibited by 3D series elements. And so manganese exhibits oxidation states of +2, +3, +4, +5, +6 and plus 7. Then from iron onwards, the maximum oxidation state decreases. That is, iron exhibits oxidation states plus 2, plus 3, plus 4 and plus 6. Because here afterwards, the minimum oxidation state is the number of electrons present in 4s orbital, and maximum oxidation state is the sum of electrons present in 4s orbital and the unpaired electrons present in 3d orbital. Therefore, for iron maximum oxidation state is plus 6. 2 from 4s and 4 from 3d. Cobalt maximum oxidation state is plus 4. Cobalt maximum oxidation state is plus 5. Plus 5. Nickel maximum oxidation state is plus 4. So it exhibits plus 2, plus 3, plus 4 oxidation states. Copper exhibits oxidation states of plus 1 and plus 2. And zinc exhibits only plus 2 oxidation state. This is because in zinc all the electrons of d orbital are paired. So it does not contain any unpaired d electrons. So only the number of electrons present in 4s orbital are involved in bond formation. Therefore, zinc exhibits only plus 2 oxidation state.